All right, folks, let's start. Hello, everyone. This is Dr. Yuzo. This is ECE 341 Power System class, and today is our very last lecture for this 24 semester, 27th lecture. Can you guys hear me well?
Yep.
All right, thank you. So we can move on. Only one thing left in this module, the renewable energy system. It's about the characteristic curve for the wind system, for the wind turbine. Okay, now let's learn how to read the curve here. Before this curve, I want to kind of summarize what we learned from the solar. Okay, so you can try to think about them in the same pattern, the solar and wind. The solar wind, the characteristic curve are respectively what? The solar characteristic curve is whom versus whom? Anyone remember? Volt current. Okay, good. It's a volt versus right. In other words, x-axis is voltage, y-axis is current, and it looks like this. It looks like this. It looks like this. And then for different radiation, we have different multiple curve. With the increase of the radiation, of course, we have the IV curve shift up, right? This is the characteristic curve. Okay. And also, you need to remember the power and how to find the power from the curve. First, the power is very easy, just equals to the product between the voltage and the current, right? And also, if you're looking for the power curve, it looks like this. It looks like this. Right. And also for different radiation, power versus output voltage. So you're controlling your output voltage to achieve the what we call this?
Maximum power point.
Very good. MPP, maximum power point. Yeah, we are trying to achieve this. Okay. Right. So by once again controlling the output voltage, this guy. Okay. By controlling the output voltage. Remember this. Okay. And today, let's talk about the wind. Following the same pattern, we're trying to figure out the characteristic curve and also the power. Okay. So the characteristic curve for wind turbine is whom versus whom. You guys have any idea, actually? Any thought? Speed versus voltage from Kevin? Well, nope, not exactly. Any other thought? Because one truth answer is power versus what?
Velocity.
Velocity is close, but actually it's talking about here. Power is something somehow in terms of velocity, speed. However, this this characteristic curve is not power versus speed. It's essentially what versus speed? Anyone can come up with something else? This is a rotational system. So it's what? Speed and what? Anyone can have anything? Excellent. Neil have the answer. As the torque, okay, everybody, yeah, as the torque. Characteristic to this rotational system means the torque versus speed. Remember this. This is also the same thing for a machine. Any electrical machine, if you study the characteristic curve, it means the torque versus speed. The torque versus speed. It looks like this. Okay, it looks like this. Also looks like this. And here, because instead of the solar, this is what different radiation. Radiation 1, 2, and 3. And these three curves also correspond to radiation 1 through 3. Here, 3 curves. What's the difference? Obviously not light radiation anymore. What is it? Efficiency? No. They're not talking about efficiency. No. They're two different what? Something in nature, right? Look at here, the same pattern. This is what I'm trying to emphasize. That's why I summarize them together as well. This is something in nature, radiation in density, determining different IV curve. This is different what in nature, determining different torque versus speed. Characteristic curve. What's nature power making them different? Anyone? Wind speed, excellent. Anil is answering this greatly. Again, okay. With different wind speed, you're gonna have different characteristic curve. This is nature power. This is something we have no control over, right? Just like the radiation. Can you control the light radiation? Doubt it. Right. So here is, once again, rotational system is, we are studying the torque versus speed. Torque versus speed. Okay, this is the torque versus speed. Then move on to the power. The power of the rotational system equals to what? In terms of speed, obviously. Anyone knows? Power equals what? Once again, we hear, if you never learned this before yet, however, you can see the pattern, right? Exactly. That's torque times speed is equals to power for a rotational system. Okay, torque times speed equals to power. And if you try to see the power, because eventually, like in the solar system, we always try to achieve the MPP, right? So in the wind, same thing. Just the power curve looks like this. It's close to the torque curve, but it's different. It's different. Okay, this is, and MPP are here and here for different, again, wind speed, right? For different wind speed. Does it make sense? This is how we rate the characteristic curves. The given might be torque versus speed, might be power versus speed, might be both. Same thing in the solar, might be I versus V, might be P versus V, or maybe both, right? This is, here, I'm showing the same pattern, right? Can you see that? The same pattern. Okay, same pattern. And of course here, the unit here, this is the ampere. Okay. This is the volt. This is what? What's the unit of P? Watt. Okay, watt. Watt. And here, watt for P again. Then what is omega and the T here? Omega might be given in hertz, might be given in radian per second. That's true. However, if you're doing calculation, it is what? Omega. Radian per second. Okay, they use radian per second. To the torque, as Kevin mentioned, is Newton meter. So be careful with the unit. Be careful with the unit. And this is so-called same pattern between two renewable energy systems. And if this is clear, then go back to this curve, this wind turbine curve. And what you see here is not torque versus speed, but power versus speed. And also be very careful. Power is fine in watts. However, what is speed? What is the unit of speed? Anyone know what is this? RPM, right? RPM is more popular used. Revolutions per minute, exactly. Revolution per minute. So this is not a radian per second. Be very careful. Be very careful. Be very careful. By the way, what's the conversion? You say this RPM to radian per second. What is the conversion formula? Anyone else? What is the conversion formula between RPM? Basically, Kevin is right. So we can write in this, right? So RPM value, whatever it is, RPM times pretty much pi over 30. The kind of a coefficient times this constant equals to radian per second. Did this look okay? How about that? RPM times pi over 30 equals to the radian per second. Okay. This is the conversion. This is the conversion. Yep, as Neil mentioned, divide by 60 and then multiply by 2 pi. Okay, same thing. This is how we find out the our radian per second for calculation. If needed, right? Well, let's just study. See. So I'm showing you this curve. Obviously, up to how many wind speed cases? How many curves? How many? N. Yep, many. Too many, right? That's actually N equals to 11, right? Yeah, since we need to read legend here. Okay, legend, different color representing different IV curve. So I give you guys 3 minutes or 3 or 4 minutes to find. Listen carefully. When wind speed equals to 10 meter per second at wind speed of 10 meter per second. Now tell me, what is the maximum power? Maximum power at wind speed of 10. What is the maximum power? And what is the corresponding torque? Obviously, maximum power means the maximum. I'm sorry, maximum power means optimal torque, right? By optimal torque, it's not necessarily means the maximum torque, but the optimal torque, which gonna give you the maximum power. Okay, remember this. It's not necessarily maximum torque. We are not looking for maximum torque. Maximum torque means nothing to us. We're looking for the maximum power. So I'm asking, what is the maximum power at wind speed of 10? And then what is the corresponding optimal torque? Well, Kevin is worrying about how many curves in the exam going to be given. No, it won't be this many, but there will be some. And there's another way to solve this issue, because you see, you don't need to worry about the color. However, you see the wind speed is from 1 up to 11, right? So the 1, 2, 3, maybe 4 and too low down here. You don't need to worry about it. However, the top one is what? Can you tell me that?
Okay, so they are, and that's what I kind of figured was they were in order. So I was guessing that it was the second one down, but I wasn't sure because I couldn't color match.
Well, obviously here we don't have to color match. Yep, the highest wind gonna give you the highest curve. That makes perfect sense. Okay, that makes perfect sense. No exception. And here, John come up with the answer here is 63 watt, correct, and 230 RPM, correct, and therefore 2.62 Newton meter, correct. Okay. Once again, the question is at wind speed of 10, you should end up with these values. Okay. Maximum power is 63 watt. Optimal at that operation point, the turbine speed is 230 RPM. And therefore, the corresponding optimal torque is 2.62 Newton meter. That this is obviously indicating you know how to read the given curve. Okay. Take a look to see any questions. Anything about this? As long as you know how to read this, and then that's enough for the exam. How to read. Here I have a question here. How do you get the 2.62? John, must convert RPM to omega. Yep, that's the key. If you have done that, you'll be okay. MPP equals to omega times t, then solve for t. Thank you, Sawyer. Do those help, Jacob? All right, good. Any other questions? Any other thoughts or inputs? Because our lecture is done. Okay, our lecture is really done. Are there any questions regarding this module or exam? Anything? Any other questions?
What was the peak line for on the wind's power to turbine speed graph?
Peak line.
We had like an orange line that went straight up through all the other ones.
Oh, here.
Yeah.
This is called peak line. And peak lines. Anyone knows what this line is? Here.
Doesn't that just go through the MPP on each curve?
Exactly right.
Oh.
That's a curve fitting for all of the MPP. Curve fitting by connecting all of the peaks of each power curve, and you come up with this. And if you use a mathematical function to roughly represent this curve, peak curve, what is it? Anyone has any idea? Exponential? No. Why exponential doesn't work? X cube close. X cube is close actually. X cube is close. X cube I think is very close, but generally speaking is S cube, or between S cube and X square. But X obviously is omega. So S cube is very close. S cube is a good answer. By the way, what does the exponential look like? Why it is not exponential? Omega, right? This is omega. Basically, the curve is like this, and this is omega cube, and maybe you have a gain in front of it, k omega cube. That's going to be make it even better. Okay. However, why is not exponential? Exponential means this. Exponential intersecting with y axis at 1. This is exponential. Okay. This is exponential. This is exponential. So this means you have an offset at 0 speed, which obviously not possible. Okay. And the generator is not spinning and you have a output power. That's not realistic. It's, free energy. Yep, free energy. And then guess what? We quit. Okay, we quit here and establish a company. Call it Kevin Zoe, and then we become millionaire or billionaire next week. So, any other questions?
Are you gonna upload the PowerPoint?
Absolutely, I have.
Oh.
Yeah, you could check right now and then confirm, please.
Yeah, I got it.
Yep, thank you.
So for the example that's returning on our final examination of the three-phase power, with the loads, are you going to give us the lead, like the voltages of the generator in terms of Y or delta? Or are we just going to assume like Y and that we're given phase-to-phase leads when you give us a voltage of the generator?
Well, that one is the, first of all, in the figure in the connection figure, I'm gonna show you the connection, right? Connection, generally speaking, the source is Y connected, so the source is connected, and the given voltage is a line, source line voltage. Source line voltage. And then it is Y connected, so you know what to do next. Okay. Because the first step is obviously to find the per phase circuit, right? In per phase circuit, you know how that's the source phase voltage. You do the similar thing. You're giving the source phase voltage 0 degree as a reference, and don't forget to divide by square 3, right? That's the per phase circuit.
Okay.
Yep. Any other questions? Wind turbine, how to find the value at 10 meter per second. First of all, 10 meter per second, that's wind speed, okay, which means the second curve here, I'm showing you here. And you don't have to worry about the color, and the 10 millimeter per second is obviously for second curve from the top. So the top one, the very top one is actually 11 meter per second curve. And right next to it, the second one is the 10 meter per second wind speed curve. Right? So first of all, you need to locate this curve. Reading the maximal power. Maximal power, obviously, this point here, right? The maximal power means maximal power at the top. You read along the y-axis, which is about 1/3 between 60 and 70. So you end up with 63 watts. And then you read corresponding the speed and go down, right? You need to go down, and then you intersecting with x-axis at this point about. If you read it, I will say this is 230, around 230, because it's more than half between 200 and 250. In the half is obviously 225. So a little bit more than that is 230. Okay. 230 is RPM, and 230 times pi over 30 equals to the radians per second. That's the speed. And then your power 63 divided by that, the number equals the torque, which is the optimal torque. It's not maximal torque, okay? Remember this, it's not the maximum torque. It's just like when you achieve the maximum power, you are not achieving maximum voltage, you're not achieving maximum current either in solar. Okay. So that's how we got those results. And here, all right, sure, no problem. And here, and their question is for question 2, the transmission line. Do you know if we are going to be given phase or line voltage? The given voltage, generally speaking, is always line voltage. Okay, three-phase system, the given voltage is always line voltage, except otherwise being told. Okay, it's always line voltage. You have no access to the neutral, so three-phase system, the voltage is line voltage. You can only measure the line voltage.